This is a review of some of the basic ideas around pointers in C. I've found in the past that students, although they probably have had some exposure to pointers in other courses, may have not really understood them or may have forgotten the details, and so this is just kind of a refresher on pointers. Remember that the basic idea of a pointer is that it's the address of something in memory. So everything that's in a C program, in any program, is going to be allocated in memory someplace. And in C, we can explicitly ask the program to tell us where something is stored in memory. So one part of knowing about pointers is knowing how to take the address of something. And the other side of it is, once we have the address of something, how can we access the data that's stored at that address, or how can we update the data that's stored at that address? So I want to just work through some example code here that illustrates some of these ideas, and hopefully as students maybe have additional questions, I may update this source code or update this video to have some more details, but this will give us a good start. So here's the source code. I'll make it available online. I've got some things in here that are just sort of some bookkeeping and some output. So I've got a little banner method, and then this function I'm not going to go into in detail, but it basically just dumps the contents of some location of memory. So you give it a little message that will print out, and then a pointer to the first byte that you want to dump out, and then the size is the number of bytes that you want to dump. And you can see an example of the use of that over here in my terminal window. So here's a pointer to an integer that's just allocated locally. We'll come back and look at this in more detail, but it says here that I've got 4 bytes that start at this address. And with the exception of the byte count, all this output is going to be in hexadecimal. So there's the hex address, the starting address, and then as you can see here, I've split these things into 8-byte chunks. So this particular case, I've only got 4 bytes, so I only have one line of the output here. I've got the address, and then the 4 bytes that are at that location in memory. So that's what this dump function does. If you want to look at it in a little bit more detail, it might be instructive to kind of see how I go about doing that, but that's not really the principal focus of this video. First thing to remind you of is about the size of operator. This is something provided by C that lets us take pretty much arbitrary data types, hand them to the size of function, and the compiler will replace that with the number of bytes that are occupied by that data type. And just to remind you how that works here, I've just created some printfs here that print the size of the various primitive types. So size of char, short, int, long, and void star. You'll remember that void star is kind of the most generic type of pointer. So if you don't have a better type to use and you need to have a pointer, that's what you should normally see. In older code, which you might see around still, it used to be you'd use char star for that purpose, but void has been around for a very long time, so hopefully you should use void star for a generic pointer, and hopefully most code you encounter will be updated in that way. The output from that function is right here. So we can see on this machine, it's just an Intel processor. The size of a char is 1 byte, shorts are 2 bytes, ints are 4 bytes, longs are 8 bytes, and pointers are going to be 8 bytes on this machine because it's in a 64-bit processor. So we're going to use that size of operator in a variety of different places here to try to get at the size of some underlying structure, but I wanted to just recall what that, or how that worked. All right, here's the basic idea of pointers. So we've got in this function an integer variable called an int, and I've initialized it to the answer to life, the universe, and everything in hex, of course. And then I've declared a second variable here that's going to be a pointer to an int. So to declare an ordinary integer or long or short or whatever, you just use the type with no additional decorations. To declare a pointer to one of those things, we use the underlying type name and then the star as the prefix to the variable that's being declared. So that an int p is a pointer to an integer. That underscore p at the end is a common but not required suffix to put on a pointer, just to kind of distinguish it from other things. So what we're going to do here is just print out some information so you can follow along over here on the side. This is the output from this function, and you can see that in the the value of an int, right, which we've initialized to 42, shows up here as 42. So I'm printing this out as a hex value. That's what the %x means here. And the prefix digits just basically mean print a 2-digit field and fill on the left with zeros if you need to. So we don't need to here, we just get that 42. So that's nothing more than just the initialization here. Now the next thing we're going to do is take the address of that an int variable. Currently, an int p, the pointer, doesn't have a value. We haven't initialized it to anything. I wanted to sort of save that as a separate operation. So the next thing we're going to use is the ampersand operator. That's the address of operator. So here we're saying take the address of an int, right? So wherever this thing gets stored in memory, and we know from ICS, for example, that local variables or automatic variables in C get stored on the stack normally. So somewhere on the stack, the compiler has allocated space for this particular variable, and we want to get the actual value for that at runtime. So for the location of that at runtime. So the ampersand operator gets the address of that variable and it stores it in this pointer. Again, an int p is just another local variable, right? It's large enough to store a pointer to something. It's initially doesn't have any value, and here we're just giving it the value that corresponds to the location in memory of an int. And we can see here in the output that the location that an int is stored at, in other words, the contents of an int p, is this hexadecimal address. So you can see that that's pretty high in memory, and if you recall, the usual process model in Unix or Linux is that the stack is allocated in high memory and grows downward toward the rest of the process. So this is a high memory address, which intuitively makes sense in that that's been allocated on the stack. So now we can make use of that an int variable by dereferencing the pointer that we've initialized here to hold its address, and that's what we're going to do next. So in addition to using the star as the means of declaring a pointer, we also use the star as an operator to dereference a pointer. So the pointer itself holds an address, and what we want to get access to is the thing that's stored at that address, or the thing that the pointer points to. So here's an example of doing that. We're taking, again, that an int p, and now we've got a prefix of that star. So we're saying now, I don't want to update the pointer itself. I don't want to update the address. I want to update the thing that the address is pointing to. That's what the star does for us. And I've now changed this to be hex AB. And if we look over here, the value of an int, instead of being 42 like it was at the beginning, is now AB, because we stored a value, this value AB, at the location pointed to by an int p. Okay, so that's really the bread and butter of pointers. You've got some variable or other location in memory that you want to have the address of. You declare a pointer to that thing. The type has to match. It's got to be a pointer to an integer in order to take the address of an integer. Then you use the address of operator to get that location. So an int is an ordinary int. We want to get the location of an int in memory. We use the ampersand to grab that, and then we store the address in this pointer variable. Then later on, when we want to access an int through the pointer, we use the star as a prefix on the pointer variable, and that says, give me the thing that this thing points to. And we know because it's a pointer to an integer, it has to point to an integer. And then we can use that on the left-hand side of an assignment statement or the right-hand side to access the value. Here we're updating it. And then we can see that that actually has changed the value stored at the location pointed to by this pointer. Next, let's take a look again at some of the places where we might find variables being allocated. As I mentioned, the local variables inside of a function, or the automatic variables, are going to be allocated on the stack. And just to illustrate that further, here's another simple example where I've got basically the same declaration here going on, where I'm taking and defining an integer variable called an int, and then I'm grabbing the address of that and storing it in an integer pointer. And then I'm going to dump out the memory at that location, the location that I'm pointing to, which is going to be where that int lives. and I'm going to print out a size of int bytes. So that's what's showing up here in the output. I've got 4 bytes that are showing up at that address, and here's a little repeat. There's the address, and there's the integer that contains the value 42. So we initialize this local variable, and we can kind of tell that it's a local variable because it's on the stack again at a fairly high address in memory, 7FF, so quite up near the top of the address space. The location that we're using here as the value where we start dumping bytes is the value of the pointer, right? The pointer has the address of an int. That's what we got, or what we calculated here with the address of operator. So by passing that address into my little dump function here, it prints out the contents of memory, 4 bytes starting at that location. And you can see that the value that's stored there, it's 4 bytes long, which is the size of an integer, and it's got the value 42 in it. It looks a little odd here, but remember that the Intel architecture is a little endian model, so the least significant byte shows up at the lowest address in memory, which is why the 42 shows up here rather than where you might expect it to be over here. And that's going to be the case throughout this whole thing. All right, let's look at the next example, which is a pointer to some static memory. Now, this is something that you may not have made a ton of use of in your C experience, but if you declare a variable that's not inside of a function, which is what I've got going on here, I've got a declaration of a static int, and I've called it a static int, and initialized it to 42. That's not part of any particular function, and in particular, it's not, because it's not in a function, it's not going to be allocated on the stack at runtime. Instead, the compiler is actually going to allocate space for it in a static location that will be allocated and initialized at the time that the program loads into memory, and that particular variable isn't going to move any place after that initialization. So we're initializing it to 42. We don't have to do the initialization, in which case the location is still allocated but just has garbage, but we're going to initialize it to 42. And then inside this little function, I'm basically doing the same thing as previously. I'm taking the address of that statically allocated integer and storing it in a pointer to an integer. And then I'm printing out the 4 bytes, the size of int bytes, at that pointer. So that's the next thing in the output here, a pointer to a static int. And as you can see, the contents is exactly the same. It's still 4 bytes wide, and it's got a value 42 in it. But notice the address. Right now we're at a much lower address in memory, and if you'll recall the process layout for a Unix process, it's usually the code section, and then initialized data, and then the heap, and then the stack. So initialized data is where this static integer is going to be stored. So you can tell that it's quite a lot lower in memory than where the stack is, way up here at hex 7FF. It's quite a lot lower where the static information is. So my point here is that, well, it's good to refresh our memory about where these things live in memory, but we can use these same operations whether we're talking about a local variable that's on the stack, a static variable that's on that's in initialized data in our process. Another place that we can allocate storage is on the heap, right, which is between the initialized data and the stack, and the heap grows upward in memory. Recall that the heap is for dynamically allocated storage using malloc and free typically in our C programs. So here's an example of allocating an integer on the heap. So here I've got the malloc function call, and I'm trying to allocate enough memory to store an int, so I don't use a hardwired constant here. I say size of int, which we know in our case here is going to be 4 bytes. And then we're going to store the resulting address in a pointer. Okay, so this is, we're getting an address of something, and just like before when we took the address of a static variable or a local variable, we need to have a pointer that's of the appropriate type. This is a pointer to an integer, and that's what we're allocating in memory here. The other little twist in this statement is that we are casting the return value from malloc to be a pointer to an integer. So without this int star in the parentheses, the program would still work, and it would still compile if you kind of dialed back the warning level on the compiler. But strictly speaking, it's not quite correct in the sense that malloc because it's a super generic memory allocation function, it actually returns, or it's declared to return a void star. So although a void star is supposed to be super generic, if you dial up the compiler warnings to a high enough level, it'll complain about that. So in order to get the compiler to shut up, you're basically saying, hey, I know that malloc returns a void star, but I'm using that as a pointer to an integer. So by putting the cast in here, you're telling the compiler, hey, I know what I'm doing here. Go ahead and let me have this code the way I've specified it, and don't worry about the fact that malloc returns one pointer type and I'm storing it in a different pointer type. I should point out, by the way, that when I'm compiling these things, let me show you my makefile. Not very sophisticated makefile. I'm using two flags to the GCC compiler. And you don't have to include these things, but what I find is that if I don't put them in, I will make a stupid mistake having to do with types or casting or pointers or something like that. And the compiler is just really good at helping you make sure that you get all of the tracks to line up properly with the addresses and so forth. So the -w all, so -w means warning, -w all says dial up the warning level to the maximum extent. So anything that the compiler sees that it thinks is a little out of the ordinary, it will give you a message about that. And if you can get the compile under the w-all flag to be a clean compile, that gives you just a lot of confidence that you've got things set up correctly. It's not a guarantee that it will work, but if you don't get rid of all the warnings, it's pretty much a guarantee that you'll have some problems at some point. The other thing that I like to do, you can use just w-all, in which case it'll give you a bunch of warnings, but if the warning isn't severe enough, according to the compiler's estimation, it'll still compile and still let you run the resulting file. I figure that I want the compiler to be totally happy with my code before I even bother to try to run it. So the -w error says, hey, treat any warning, no matter how minor, as an error, as something that will not result in the program compiling to an executable or to an object file if you have multiple files. So I strongly recommend, especially when you're learning stuff, and I've learned this stuff a long time ago, but I still use these flags because I just make mistakes. So include those two flags in your compile in order to give yourself the maximum chance of getting it correct. Okay, back to the code. So again, because I'm using w-error and w-all, that's why I've got to put in the cast here to get the compiler to recognize that I know what I'm doing. So all malloc does is allocate space for you to store your own information into. It doesn't do any kind of initialization at all, so whatever happens to be in the heap at that location in memory is going to be what's showing up in that variable in this case. So the next thing I'm doing here is initializing the memory that I just allocated and setting it to 42 again, and I'm using the same kind of syntax as we saw before for the basic ability to make a change to memory through a pointer. So an int p is a pointer to an integer. It happens to be happens to point to memory that was allocated by malloc, which is fine. And now we're saying, hey, at that location, dereference that pointer and store at that location the value on the right hand side. And we can see here when we dump this out, so pointer to heap int, that's right here. And you can see again it's 4 bytes starting at this address, and it's got the value 42 in little endian byte ordering. You can see here that this address is also pretty high up in memory. That just happens to be where the heap lives right now. Notice though it is below the location of the stack by a fair amount, and it's above the location of the statically allocated storage that was created by the compiler and loaded and initialized at the time the program got started. The other thing, of course, that you need to do when you're using malloc to avoid a memory leak is to free the allocated space. It's also important to keep in mind that after you do this free, which basically takes that location in the heap and returns it back to the dynamic memory allocator, you may still have a value stored in this pointer, right? But after you free that memory back to the operating system, it's really a bad idea to try to access data through that location, because it's no longer allocated to you. It may just have garbage in it. It may, at some point in the future execution of your program, be allocated in a different place, and now you've got multiple pointers that point to the same memory that you don't really want to get run afoul of that situation. It's just a recipe for disaster. Let me show you a similar allocation here, except rather than doing an integer, we're going to look at allocating a long. So here's the output from this little function, and pointer to a local long. And this is exactly the same, except I've swapped out the integer from up here for a long. So I've declared a long. Here's a pointer to a long. In order to be able to store the address of a long, I've got to have a pointer to a long, or the compiler will grouse at me. So again, the star in the declaration says this is going to be a pointer. The ampersand takes the address of this long and stores it at that location, and then I'm printing out the result. And you can see in the output here that I've got, again, up in high memory, I've got 8 bytes that have been allocated on the stack, and what's stored there is the long integer version of 42. So it's 8 bytes wide instead of 4 for an integer, but it still just has that little endian encoding of the value 42 stored in it. Let's take a look at arrays. And I want to remind you again from previous classes where you've learned that an array in C is really just a pointer under the hood. So the address of an array and the location of that array's first element is the same thing, right? So you can use the array syntax with the square brackets and stuff, but the compiler is basically converting that into pointer accesses and pointer arithmetic behind the scenes. So knowing how to use the pointers directly can be a real boon when you need to be able to do something in more detail, but it's still sometimes helpful to be able to have the array syntax as well. So I'm going to declare a constant called n here, so I don't have a magic number, and then declare an array. Right, so this is the standard C array syntax. I'm declaring an array of integers. I'm calling it an int array, and I'm saying this is going to be n, or 5 integers long. So again, this is a local variable, so it's going to be allocated on the stack. The compiler will arrange for code to be generated that allocates enough memory to store, in this case, 5 integers. Now, the first thing I'm showing here is how do we compute the size of that array. There's kind of 2 ways to do it commonly. In this case, because we're statically allocating the entire array on the stack in one statement, where we know the compiler knows that there's going to be 5 integer-sized things allocated there. So when we're interested in figuring out how big that is in our code in an independent kind of way, we can ask for the size of that actual variable, an int array. And as you can see over here, we get back as the return value 20 bytes, which makes sense, right? Because an integer is 4 bytes times 5 integers is 20 bytes. The other way to do this is to, instead of having an array that we know the size of, or that the compiler knows the size of at compile time, if we have an unknown number of elements in that array, for example, because we've calculated this appropriate size of the array, or we've read it in from a command line parameter or something like that, we can also take the number of elements times the size of each of the element. So in this case, size of int, again, is going to be 4, and here we're going to have 5, but that could be a variable instead of a constant. And we could dynamically allocate as many elements of the array as we want, and this would give us the appropriate size information. So the resulting array that we're going to get is shown in this next dump. And notice I've put in a comment that says this has not been initialized. So whatever just happened to be on the stack in this case, in the location where the compiler ended up generating code to allocate this memory, is what we're going to see in the array. We haven't set it up to have any particular value, so it kind of all bets are off. And you can see by looking at this dump, it's just, maybe there's something recognizable from a previous stack frame or something like that, but we can't guarantee the content of that array at this point. So the next thing to do, the next thing to do is to initialize it. So that's what I'm got going on here, in an int array of I, and I'm allocating, or I'm assigning a value 42 plus the index in each of the elements of that array. And then we can see here after the init, that's what we got shown here, we've now got 42, 3, 4, 5, and 6 being stored in that array of 5 integers. Okay. Again, it's important to keep in mind when you're dealing with arrays that an array and the address of its first element are really the same thing. Okay. Behind the scenes, there isn't any such thing in the assembly language that's generated as an array, right? There's things in the processor architecture that can help us with that, the sort of load effective address style calculations and so forth with indices and offsets and the like. But the CPU itself doesn't really have as high a level view as thinking of arrays as such. So C compiles the array instructions down into something that basically is just doing pointer manipulation, which is almost exactly the same as what takes place in the CPU. So to illustrate this notion that the array itself and its first element's address are the same, you can see this output here. So I'm taking here's the an int array that I declared up above, and I'm just printing that thing out. The %p is the way that you tell printf to just print an address. And you can see that this is 7ff ... 70. And furthermore, if I take that integer array and I ask for the 0th element, right, the first element of the array, and then I take its address and print that, you can see here in the output that it's exactly the same thing. Okay, so I can either access an array by using the standard array syntax in C, or access it as in a pointer to individual elements, or in particular here the very first element. Either is totally fine. Here's another example where I'm showing the ability to basically find the address of any element in the array. I've got a little for loop that's iterating over all the array indices and then printing out the index, the value that's stored in the array at that index, and then the address of the array element at that index. And the output shows up over here. You can see that the values are as advertised previously, right? 42 through 46, as we saw previously in this dump of the memory. And you can also see that the addresses are available to us by using the ampersand operator over here. And it's also good to note that because the individual elements of the array are 4 bytes wide, right, they're integers, we can see that the addresses that we're printing out for consecutive locations in the array also go up by 4, so 0, 4, 8, C, and then back to 0. That reflects the notion that those array elements are packed right next to each other, 4 bytes at a time, and that's what we're seeing here in the output. We also want to be able to manipulate structures and think about pointers to structures and the elements of structures. Here's a simple structure that I've defined that we want to take a little bit closer look at. Remember that integers are 4 bytes wide and longs are 8 bytes wide in an x64 architecture. The structure, as I've written it here, has an integer array of 3 integers. So that's going to be the first 12 bytes of the structure. And we know that structures get manipulated a little bit by the compiler in order to keep everything on the proper alignment restrictions. And we know that the structure itself as a whole will match the alignment of the longest element within it. And that happens to be this long integer, or unsigned long, that I've defined here as the second portion of the structure. So the structure itself is going to be aligned on an 8-byte boundary because that's where its longest structure needs to be aligned. But these 3 integers that are going to be ahead of that long are only going to take up 12 bytes, which means that we're going to have 4 bytes, sort of the, what would be the 4th integer that we're not really using here, 4 bytes that are going to go unused. So in terms of kind of just the basics of this structure, here I'm allocating a structure using this typedef. Remember that typedef allows us to take an ordinary declaration or definition like this structure declaration and give it kind of an alias. So instead of having to write typedef struct to declare variables of this type, I'm now able to just say a struct t. And the convention, kind of like with p for pointer, is to use a t as the or underscore t as the suffix to indicate a type. So in my first function here, I'm declaring something that's an a struct t, so one of those structures, and I'm giving it the name one struct. Again, I could have just as easily have said type def struct one struct here instead, but I prefer the type def. Once I've allocated that, and this is going to be, if you think about what's going on here as far as the compiler is concerned, the compiler is going to make code that will allocate space for this structure on the stack. It's a local variable, an automatic variable. And then once it's been allocated, I can fill up the contents of the structure's elements. So saying one struct dot an int array of 0, an int array of 1, an int array of 2, and initializing it to those three values. And then I'm initializing the along thing to A, B, C, D, and so forth. Notice that because I have an actual instance of the structure, the way that I refer to its elements is just using the dot operator. And we'll see in a second that when you have the structure itself, you use the dot to access its members. But when we have a pointer to a structure, we're going to do something a little bit different, typically. So here's the contents of that structure. So single struct. Here's the output from that dump. You can see that the amount of space that's dumped out here based on the size of that one struct that I've got here is 24 bytes. So the first 12 bytes are those three integers, and then there's some padding that's added to keep everything aligned properly, which pads these this first group of integers out to 16 bytes, and then that long integer occupies 8 bytes, which gives us a total of 24 for the structure. So I didn't point this out previously, but just keep in mind that that size of operator works great for structures as well as individual primitive data types. And you can see here that the memory that's being dumped shows the value 42, again an integer in little endian encoding, 43, 44. Here's the padding, hasn't been given any initial value. Whatever happened to have been there at the time that the compiler or the compiled code stuck this on the stack is what you see. And then the last piece here is A's, B's, C's, D's, and then dead beef spelled in little endian sequence. Okay, so that's an individual structure. We're going to see that we will also be able to allocate arrays of structures. So if we want to have more than one of those things, we can do something like this. So here's a struct t again. That's the type def. So we could also have said, back up here, we could have said instead type def struct, but I'm using the type def. And then I've got a variable called a struct array, and I'm saying let's make an array of 3 of those things. So when we dump that out, we can see that we now have 3 times as many of those structures in our memory dump. So I haven't done any initialization on this yet. So the contents of the memory here is just whatever happened to be on the stack at the time. Notice also that because I have declared a static array of 3 of these a struct t structures, that I can have the compiler tell me how big that is by just saying size of a struct array. If I was allocating these dynamically, just like before when we were talking about dynamically allocating an array of a primitive type, I would be able to say size of a struct t times the number of elements that I had allocated. Now I'm going to call this function init struct array, which is going to initialize the structure that I had declared here, and then print out the same memory location, except now after initialization. So here's what that looks like, and I'm using a similar kind of way of initializing this, say 42, 43, 44, and then a little different value for the long integer. And then here's the second group of, here's the second structure with 52, 3, and 4, and different values here. I guess they're the same values. And then here's the third element of that array. So each of those elements is itself in a struct t, a 24-byte thing that's defined by that structure. Let's take a little bit of a look at the way that this initialization function works. So first of all, Let's look at the arguments that we're passing. Well, the second one is kind of easy to understand. I want to be able to tell that initialization function, hey, I've got 3 of these things stored together. And then I'm passing in a struct array. Again, because the variable itself is, in fact, a pointer to the beginning of that array, that's exactly what I want to pass here. I could also pass the address of the first element, but that's more syntax, more work when I know already that array types in C are really just pointers to their first element. So this is the pointer to the beginning, and this tells me how many of those structures I've got lined up after that. So here's the initialization function, and the way it's declared again, because I'm passing in a pointer to an array of a struct t's, that's the way I've defined this thing here. It's an a struct t pointer, and I've just called it s underscore p here for simplicity. And the second argument is just an integer n that says here's how many elements I have stored at that location of type a struct t. So my initialization basically is just nested for loops. I want to initialize each of those n structures, and then within them I want to initialize the 3 integers that are the first portion of the structure, and then finalize that by initializing the long value in each structure. So here, the syntax to access these elements, I've got s sub p, which is a pointer to an individual structure. But because I have an array of those things, I'm using the array syntax to dereference either the 0th, the 1th, or the 2th element of that array. And then once I have that information, I use the dot operator to grab the individual elements of the structure. The first one, of course, is itself an array, so it also needs to be dereferenced with this index to access each of the 3 elements in that array, and then I just initialize them to slightly different values depending on which element of the structure or which element of the array we're talking about. And then I've done something similar with the long, and I just chose to initialize that to the same value each time. So that's how these guys, this one over here would be the third, so it would have started out at 62, 3, 4. This is uninitialized here. It's just that padding that was created by the compiler, and then there's the little endian encoding of that final long value. Finally, I want to talk about how to access structure elements directly or through pointers. So this final example, I've got an instance of a struct t called a struct, and then I'm also taking the address of that thing. So here's a pointer to an a struct, and to get at the address of that thing, I use the ampersand operator like usual. So here's and I haven't done any initialization here, so it's just going to have whatever happens to be in memory at that location at the time. So uninitialized struct, that's this output, and you can see that looks like the vestigial remains of a previous execution of different functions that just happen to be on the stack in the same location, but those are not values that we can rely on at this point. So what I'm going to do is basically just set a single value from this structure. I have access to the structure itself, and when I have the structure itself, the easiest way to access its elements is to use the dot operator. So this says give me the array called an int array from that structure, and in particular grab the 0th element of that array and set it to just a, b, c, d. And you can see here in the change directly with dot output that we see a, b, c, d. Again, it's little endian encoded, and everything else remains unchanged. Okay, so if you have the structure itself, not a pointer to the structure, the easiest way to make changes to or access the contents of that structure is to just use a dot to get at the individual elements in the structure. Now if you happen to have a pointer to a structure, so let's just pretend that this a struct variable doesn't exist here, and we're going to just act as if we only had this pointer. If somebody had passed us a pointer to one of those structures and that's all we had, here's what we would need to do in order to access that. We would have to dereference the pointer to start with, right? That's what the star here is doing. We've got a struct p as a pointer, star a struct p is the thing that it points to, which would be the structure itself, and we have to wrap that up in parentheses because the precedence of the star is defined in C to be lower than the precedence of the dot, which would mean if we just said star a struct p dot, what would happen is we would be dereferencing something at a struct t dot an int array of 1, which isn't what we want to do. We don't want to mistakenly treat the first element or the second element of that array as a pointer and dereference it. We want to dereference this thing, and then once we know the location where that lives, then use the dot operator to grab the next of those integers in that array inside the structure. And you can see here in this next output that we've got still the value that we stored ABCD in the first of those, and now in the second of them we have 8765, which is the thing that we just stored here. Now that syntax, although it's not too horrible, it turns out that you pass pointers to structures around a fair amount in some types of code. And so there's a little bit of syntactic sugar that C gives us to make that a little bit easier. So in the case where we have a pointer to a structure, we can, instead of doing all this monkeying around with the parens and the stars, we can use this little arrow operator. So hyphen greater than does the same job. It says, think of the thing on the left-hand side as a pointer, dereference that pointer, and then reference this structure element within that location. So this does the same thing that this does, except it's just quite a lot cleaner, easier to understand, easier to read and code. So we can see in the final output here that we've got change with arrow, and now the third element of that array is going to be 4321, so that's what we see, 4321 here. So that's a far simpler and friendlier and easier to maintain syntax for accessing structure elements through a pointer. Again, the take-home rule is if you have the structure itself, use the dot. If you have a pointer to the structure, you can go ahead and use the arrow to simplify things and not have to do this kind of awful looking syntax.